I'm going to go through the solutions to some practice problems about sequences, summations, basic counting, and probability. I'll do it in sections, but this first video will talk about some true-false questions and maybe a couple of sequence problems. So here's a true-false question. The sum of a geometric sequence, a1 through a sub n, can be calculated as n over 2 times a1 plus an. And that's false. That is the correct formula if the A sequence is an arithmetic sequence, but it is definitely not appropriate if it's geometric. Illustrating the fact that you really got to be sure about what type of sequence you're looking at. Is it arithmetic? Is it geometric? Or neither? And of course the vast majority of sequences are neither, but we tend to focus on arithmetic and geometric because they have such beautiful shortcut formulas. For a geometric formula, for a geometric sequence, then the sum, well, first of all, that's one way to recognize that is if it's of exactly this form, a1 or a1r to the 0 plus a1r to the 1 plus dot dot dot. If you can write it as a fixed number, that's the first term in the sequence, times a fixed ratio to higher and higher powers, and if there's n terms in the sequence, notice this is the nth term, and if you write it in the standard way, it is the first term multiplied n minus 1 times to get to the nth term, because there's n steps between a1 and an. That sum is a really, really important formula. 1 minus r to the n over 1 minus r. Oh, there's no way that you're going to read that very well. Let me display that. Okay. And that's a very, very famous formula. Sometimes you'll see it written. I tend to have people, discover it with the subtractions different on the top and bottom, but it's the same thing. Okay. Two very useful formulas that happen in very different situations. Okay. A sequence is geometric if the difference between successive terms is always the same. Again, false. That's for an arithmetic sequence. For a geometric sequence, it's the ratio that is the same. One tricky thing, if you have, apropos of that, if you have, let's say, 96 plus 48 plus 24 plus 12 plus 6 plus 3 plus 1.5 plus dot dot dot, that is a geometric sequence because the ratio is always the same, and you could ask, is r equals 2? Because after all, 96 over 48 is 2, 48 over 24 is 2, 24 over 12 is 2. But, pause it if you don't want the answer. R here is 1/2. It's really important that it's the ratio of a term to the previous term. It's what you need to multiply the previous term by to get the next term. So it's the progression. This is an r equals 1/2. So this is a decreasing geometric sequence. If you had minus every other time here, which is quite possible, you go up, forward 96, backtrack halfway, forward 24, backtrack halfway, forward 6, backtrack, then there the r would be minus 1/2. Okay. Similarly, if it's an arithmetic sequence, if you have 150 plus 145 plus 140 plus 135 plus 130 plus etc., then here the difference, this is arithmetic because it has a common difference. We usually call that d, and here it's -5 because it's what you have to add to a term to get to the next term. We're always interested in creating further terms in the sequence. That's the perspective we have. And you add a -5 here. So don't get that sign wrong. A recursive formula for a sequence gives the nth term as an explicit function of n. That's what's called a closed formula. So that's very useful, but a recursive formula gives the nth term, let's say a sub n equals some function of a sub n minus 1, not of n, but of what the actual value of the previous term was. So maybe 4 times a sub n minus 1. That would be a geometric sequence, for example. And we'll see that in the next few problems. Let's see. So, let's see what we want now. Okay, let's do one more. So find the first 5 terms of the sequence defined recursively by a1 equals 2, and a sub n equals a sub n minus 1 squared. So this is a classic example of a recursive sequence that any particular term, the current term, I like to think of it as, in the sequence, is determined by doing something to the previous term. The n doesn't appear explicitly here. You don't have to know exactly what term you are at the sequence. You just have to look whatever the previous term was and you square it. So here all I'm asking for is find the first 5 terms. So a1 is 2 by, that's given. A sub 2 is a sub 1 squared, and here's a sub 1 sitting here. 2 squared is 4. A sub 3 is a sub 2 squared. Well, here's a sub 2. It's 4, so we get 4 squared is 16. Every single time you just square the previous number. So notice, like a5 is 256 squared. That doesn't have anything directly to do with 5 or 4 or 6 or anything to do with which one it is in the sequence, not directly. All you have to know is what the previous term was and do something to that. These numbers grow pretty quickly. The next one would be rather more digits, it'd be about 10 digits long. So that's an example of a sequence that grows really, really fast. This is, by the way, this is neither geometric nor arithmetic. It grows faster than any geometric sequence eventually, in fact. So yeah, so here I mentioned that this is very different from if you have some other sequence, let's say it's b sub n, is n squared. So you take the actual position in the sequence and square it, not recursive. Well, that would give you 1. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. That 25 is not 16 squared, it's the position in the sequence, which is 5, it's the 5th term in the sequence, squared. So that's a really good distinction to make between those. Here's an extra problem that I didn't put in the review. Suppose you have some other rule, a sub 1 equals 6, and a sub n is 3 plus 2 times the previous term. Okay, so that's going to be, so pause it and try it out. Well, that's 2 times that 6 plus 3, and so that's going to be 15. A sub 3 equals 3 plus 2 times, and you just look at that number. You don't, this doesn't mention the 3 explicitly or anything like that. You just plug in that number. Twice the previous term plus 3, that's going to be 33. A sub 4 equals 3 plus twice the previous term, 69. A sub 5, and we'll stop there. Not that you have to, not that there's anything sacred about that. 69. So 141 looks like. Oops, equals 141. Okay, so that's another bonus example of a recursive sequence. Turns out this is closely related to summing a geometric sequence. For example, this is what you'd have if you put in $6 into an account at 100% interest. So they double your money every time, and you keep putting in $3 extra each time. So it's related to work we did on annuities and things like that. But you can get the numbers just by iterating this rule as many times as you need to. That's good enough for this video.